Good afternoon, everyone. Welcome to this GCSE Physics live group tutorial. Today the session is on static electricity. So as usual, this will be a 1 hour session and you'll be able to watch that back as all these sessions are recorded. You can access those on our site or also on the My Tutor YouTube channel. So our tutor this afternoon is Preshayla. She studies physics at Loughborough University and this is her 4th year as a tutor, so she's got tons of experience. And as I said before, this is a session on static electricity. And I'll just wait a couple of seconds for some more people to join because we had lots of sign-ups for today's session. As usual, just put any questions you have for myself or Preshayla in the chat and we'll do our best to answer them. Don't worry if something gets missed, I'll be making a note of questions and we can come back to them at the end. We can just run through those. Brilliant, okay. Looks like we've got a good number of attendees for this. So what will be covered today, firstly, we'll be understanding what static electricity is and how it's created, understanding what electric fields are and how they're created, and then spend a nice long time on some exemplar questions. So hopefully today's session will be really valuable for you guys. And then, as I said, at the end, there'll be time for questions. So if you're all ready, Preshayla, then we can get started.
Brill. Okay, so yeah, as Tilly said, today's session is going to be on static electricity. So we're going to be going through quite a lot of exemplar questions today because there's not much content, but the content that we are going to cover can get quite tricky. So please do put any questions on the chat if you have any, because it can be quite difficult to get your head around at first. Okay, so we have this thing called static electricity, and I'm sure you've probably experienced it before when you've rubbed a balloon on your head, or maybe you've been taking off a jumper and you felt an electric shock. So static electricity is everywhere and it happens between charged objects. So here we have static electricity between two certain insulating materials. So note that it's insulating materials and only specific materials. Okay, and the examples that come up time and time again we'll see as we do the exemplar questions, but it tends to be acetate, polythene, and certain materials that allow the static electricity to happen. Now, when we have static electricity between two insulating materials, it can also be known as charging by friction. So if we have two insulating materials, and we rub them against each other in any which way, it doesn't need to be a certain direction or anything, they will become electrically charged. Okay, so when certain insulating materials are rubbed against each other, they get electrically charged. Now, negatively charged electrons, so I'm sure you've heard of an electron, which is a small kind of unit of charge, of negative charge. When we rub materials together, those electrons are rubbed off of one material and transferred onto the other. Okay, so when we have this rubbing of materials, the electrons transfer from one material to the other. Okay, now the material that gains electrons, so the material that gains electrons becomes negatively charged. So it loses, so if it gains electrons, it becomes negatively charged. So it's gaining more negative charge, which makes sense. It becomes negatively charged. And the material that loses electrons becomes positively charged. Okay, and they're equal. So the equal charge on the rod is the same as the charge on the cloth in this example. So it's kind of opposite, kind of a little bit counterintuitive, and takes some time to get your head around. So I'll just go through it again. The material that gains electrons, so if it gains electrons, it becomes negatively charged. And if we lose electrons, it becomes positively charged. So it's losing that negative charge, so it is able to become positively charged. Okay, now if we zoom in on this diagram here, we can see a mixture of charges on the rod and a mixture of charges on the cloth. Now, in between these two pictures, they've rubbed the materials together, and what's happened is we've got an overall charge on the rod of positive. So you can see there's more positive charges on the rod. There are still some negative charges, but the majority are positive. So we say that the rod becomes positively charged. The cloth has more negative charges. So because the majority of charges on the cloth are negative, the cloth is negatively charged. So the electrons move from the rod to the cloth in this instance. Okay, so that's kind of how static electricity works between two insulating materials, and otherwise known as charging by friction. So it's by that transfer of electrons that we are able to get static electricity. Okay, so transfer of electrons is very important, and it's something that's going to come up time and time again in the questions and in this topic. Okay, so now we have two electrically charged objects. So you might have two test charges, two test negative charges, two electrons, two positive charges, any two objects that have electrical charge. Okay, so they might be dangling on a string, they might just be next to each other, anything like that. We have a rule to describe them. Okay, there's a force that acts between them. This force is called the electrostatic force. So I'll spell that out. It's the electrostatic force. So this force acts between any two electrically charged objects, which when brought close together, exert a force on each other. Okay, so this electrostatic force acts between the two electrically charged objects. Okay, now if we have two objects that carry the same type of charge, that is to say whether it's positive or negative, then they repel. And if we have two objects that carry different types of charge, they attract. Okay, so if you've done magnetism at school, you might remember putting a north pole and a south pole together, and when you do so, they attract because they're different. But when you put a north pole and a north pole together, they repel because they're the same. And it's very, very similar in the electrostatic force. If we have the same type of charge, the same sign, if you like, they repel, and different, they attract. So here we can see repulsion because we have two negative charges, and here we can see attraction because we have opposite charges. So exactly like magnets, but instead of north and south pole, we just have negative and positive. Okay, now attraction and repulsion can happen between two objects even if they don't touch. Okay, so if they don't touch each other, we can still have the electrostatic force. So don't need to be touching for this force to happen. So we call it a non-contact force, okay? A non-contact force. There are other forces which are contact. So for example, friction, that would be an example of a contact force, but gravity and the electrostatic force are both non-contact. Okay. So moving on from there is electric fields. So you might have heard of magnetic fields. So we'll start off with magnetic fields. You might have done the experiment where you put a magnet underneath a piece of paper, and then you pour iron filings on top of the paper, and you get to see the magnetic field lines make a nice pattern around the magnet. And electric fields kind of do the same thing. So if we take a charge, a positive or a negative charge, just a sphere of charge, we create an electric field. Okay, so a charged object creates an electric field around itself. So anything that is charged, whether that's an electron, whether that's a positive charge, whether that's just something that happens to be charged in your home, they are going to have an electric field around it. We can't see this electric field, but it is there. We know it's there. Okay, so an electric field is around a charged object. And by charged object, we mean something that is positive or negative, not a neutron, because that would be neutral. Okay, neutrons don't have any charge, either an electron or a positive charge. And you might have heard of it being called a proton. So a proton or an electron, or just a positive and negative charge. Okay, now the way that we show these electric fields is through electric field lines. Okay, so electric field lines are closer together when we're close to the charge and further apart when we're away from the charge. So we do them in these kind of in these lines that go towards the sphere and away from the sphere. So you can see that by doing lines going outwards, we have them closer together when it's close to the charge and far apart when it's far away from the charge. Okay, so close together and far apart. So that's one important feature of electric field lines. So stronger is closer. And then the other important feature of electric field lines is the direction in which they go. So electric field lines always go from positive to negative. They go from positive to negative. Okay, that's just the convention of electric field lines. So you can see that if we have a positive charge, our electric field lines go from positive away. Yeah, they go away from positive. And if we have a negative charge, well, electric field lines go towards negative. So they go away from positive and towards negative. Okay, so two conventions there of electric field lines. How close they are determines how strong the field is, and they must always be in the correct direction, which is away from positive and towards negative. Okay, so hopefully we've kind of understood those two elements, so static electricity and electric fields. Now we're going to go through quite a complex piece of apparatus that combines electric fields and static electricity. And that's called the Van de Graaff Generator. So you might have seen one in movies, in TV, or you might have actually seen one in person for yourself or even tried it out. But a Van de Graaff generator is essentially this piece of apparatus here, which consists of a motor, a belt, and a dome. Okay, now the way that the Van de Graaff generator works is in 6 main steps. So the Van de Graaff generator removes electrons to produce a positive charge on its dome. So if we think back to the first part, when we lose electrons, we become positively charged. And that's exactly what happens on the surface of the Van de Graaff generator. So it removes electrons to produce a positive charge on the dome. Okay, so that's the first step of the Van de Graaff generator. The second step, and it's not so much a step, more of a fact about the generator that we need to take into account. is that a person does not have to touch the dome to start feeling the effects. So as static electricity is a non-contact force, as we mentioned earlier, you don't actually need to be touching it to feel the effects of the force. You just need to be in the vicinity of it and close enough so that it can affect you. Now this force, we know, acts on any charged particle in the electric field around the dome. So if a charged particle comes near the dome, it's going to feel this force. Okay, so a charge in an electric field feels the electrostatic force. And it's the same thing here. If a charge comes near the dome, it feels this electrostatic force. Okay, so if a person is stood on the ground, it is insulated from the ground. Okay, so if you're standing on the ground, you have insulation from the ground. And touching the dome of the Van de Graaff generator will also lose electrons and you become positively charged. Okay, so because you're stood on the ground and you're touching the dome of the generator, you lose electrons and become positively charged. Okay, now the same thing happens to your hair, and it's kind of weird, but you might see when people touch a Van de Graaff generator and they're standing on the ground, their hair sticks up. Okay, now each of those hair follicles are positively charged, just like the person. The hairs repel from the head and from every other strand, causing them to stick out in lots of directions. So I'll just explain that again. Their head is positively charged and their hair follicles are positively charged. Now, because we have two positive charges, they repel each other. Okay, and because they repel each other, the hair sticks out on end. Now, because each of the hairs have positive charges, they also repel all the other hairs. So we get this kind of fanning of the hair sticking out of the head because all of this positive charge is repelling each other. Okay, so Van de Graaff generator works because of this positive charge on the dome, in your head, on your hair follicles. Okay, and it's not dangerous because we're insulated from the ground, but you will feel the effects, and you will feel the effect in your hair. So it's quite a cool little piece of apparatus if you ever do get to have a go at it. So yeah, that's the Van de Graaff generator, and it combines this static electricity, which comes from the transfer of electrons. So if you remember, static electricity is all about the transfer of electrons, as well as combining it with the electric field, the electric radial field that we have coming out from the dome. Okay, so quite a kind of complex piece of apparatus that we have here, which combines both aspects of the topic. Okay, so we've kind of talked about it a little bit already, but if we were to place a charge in an existing electric field, what would happen? So an existing electric field is created by a single charge on its own. So if we have a single charge, all of the electric field lines go outwards if it's positive, and they all come inwards if it's negative. Now, what would happen if we were to place a charge in that existing electric field? Well, if we place a negative charge in a positive charge's electric field, they're going to attract. And the same thing. So remember, different charges attract, like charges repel. Okay. Now, it's going to feel that electrostatic force. Any charge that is placed in an existing electric field feels the electrostatic charge, the electrostatic force. And again, the force gets stronger as the distance between the objects decreases. So if we're really close to the charge, if we're in the place where the field is very strong, so remember where the lines are close together, the field is very strong. Now, if the field is very strong, the charge that is placed in the field feels a stronger force. So the force is stronger as the distance between the two charges decreases. Okay, so this is all about placing a charge in an existing electric field and the force that that charge feels because of it. Okay, so we're going to move on now to some quick fire questions, multiple choice, and hopefully we can have a go at these and understand kind of the basics before we move on to the more complicated questions. So first of all, could you take 1 minute to answer questions 1 and 2? You can put your answers in the chat, or you can just have a think about it to yourself. Great, I can see loads of you getting the right answers, which is brilliant. So the charge on the electron is negative. And during the process of charging by friction, so remember charging by friction is just static electricity, which particle is transferred? Electrons. So we never transfer protons to neutrons, it's always the transfer of electrons. So the transfer of electrons is really fundamental to static electricity being able to happen. Okay, so the transfer of electrons. Cool, got 2 more here for you to try, so you take 1 minute again to try and answer 3 and 4, and by the duster here, it means the duster in the page that we went through first. Great, I can see loads of you putting the right answers. So if it loses electrons, it becomes positively charged. And the same for gaining electrons, it's the opposite. So if it gains electrons, it becomes negatively charged. Brilliant. Okay, and then for question 4, a negative charge will do what to another negative charge? It will repel. So well done if you got those answers correct. If you're struggling to kind of work out 4, just think about, go back to magnets and think about north and south poles. So like charges repel and different charges attract. Okay, just like south pole and north pole. Great, 2 more here. What will a positively charged object brought close to a negatively charged object do? And what is the volume of space around a charged object called? Okay, cool. I can see loads of you putting the correct answers in. What will a positively charged object do to a negatively charged object? Well, they're going to attract. So because they're different charges, they attract. And what is the volume of space around a charged object called? That's an electric field. Okay. Magnetic field only happens with magnets, so North and South Pole, and gravity fields are a different topic, so don't worry about them right now. Okay, the arrow on an electric field diagram shows, and I didn't exactly state the answer to this question, but hopefully you'll be able to infer it from the way that electric field lines go. And if the arrows on a field diagram are close together, the field is what? So the 7 is a little bit trickier. Okay, so I'm having all 3 answers in the chat, so let's just clear that up. The arrow on electric field diagram shows which way a positive charge will be pushed, okay? So if we were to have a negative charge, the electric field would go from positive to negative, so inwards towards the charge. Those lines are supposed to be straight, but okay, so they would go inwards towards the negative charge, and the positive charge, if you were to put a positive charge in this diagram, the positive charge would go towards the negative charge, and that's the same direction as the arrow. So the arrows on an electric field diagram show which way the positive charge would be pushed. Okay, so hopefully that makes sense. If the arrows on a field diagram are closer together, the field is stronger. That's absolutely correct. So well done if you got both answers. Not to worry if you didn't get 7. That one is a little bit trickier, but hopefully it makes sense now that I've drawn it out for you. Okay, if a negative charge is placed in an electric field, in which direction does it feel force? So a negative charge placed in the electric field lines. Give you a few more seconds. Well done if you said C. A negative charge feels the force opposite to the direction of the field lines. Brilliant. Okay, and one last one of those kind of multiple choice questions. It's a little more wordy this time. So a positively charged object is placed in an electric field around a positively charged metal dome. So our metal dome is positively charged, and these are all positively charged objects, so P, Q, R and S are all positive charges. In which position, P, Q, R or S, would the object experience the greatest force? So think about the electric field lines on this dome. So the positive charge here. So the field lines always go from positive to negative. So from positive, we're going to go radially outwards. And where the field lines are closer together, we have the greatest force. So yes, well done all of you that picked Q. Q is closest to the dome, and that is where the electric field lines are closest together, and therefore the field is stronger and the object experiences a greater force. So it would be BQ. Okay, so I think that is all of the multiple choice questions. So here we're going to be going into more wordy answers. What is kind of special about the static electricity topic is that it doesn't have much maths. It doesn't have many equations. It's more about you understanding the physical ideas behind it, the physics behind it, and the science behind it, to come up with kind of wordy answers, so qualitative answers, rather than just putting numbers into equations, which is why it can be more tricky than the other topics in electricity. Okay, so this question talks about a plastic slide, and the child that goes down the slide becomes electrically charged as he goes down the slide. Explain why this might happen. So why might the child become electrically charged when he goes down the slide? And I'll give you 2 minutes to think about the answer to this question. Well, I'm getting some really great answers in the chat. So yes, friction between the child and the slide causes electron transfer. So it causes electrons to go from one material to the other. It doesn't matter which material it goes to or from, but there is a transfer of electrons between the two materials. So that's important. So it's that friction that causes the transfer of electrons. It's that friction that causes the electrons to be removed and transferred. Okay, so I'll write that down for those of you kind of watching back. Friction causes the electrons to be transferred from one material to the other. Okay, so the key idea here is that there is friction and there is transfer of electrons. Okay, and that transfer of electrons means that the child becomes electrically charged. Okay. Okay, next question. So the image below shows a plan view of the positively charged metal dome of the Van de Graaff generator. What would the electric field pattern look like? I've kind of already given you a hint, but let's see if you can remember. What direction would they go and how would they look? So remember to draw the arrow heads on the lines. Great, I can see loads of you put in the right answers in. The arrows would go outwards and they would gradually get further apart. So as I drew before previously, I won't draw it again, but the field lines do go radially outwards, so radially outwards. And remember that when you are drawing field lines, there must be at least 4. So it's not enough for you to just go like that and that. There must be at least 4, so you must have that. To be safe, I always draw 8. Okay, with making sure you put the arrowheads on, that's one of the most important things. Okay. So the next one is a student rubbing an acetate rod with a cloth. The diagram above shows the charges on the acetate rod and cloth before and after rubbing. Explain how rubbing an acetate rod with a cloth causes the rod and the cloth to both become charged. Okay, so I can see some great answers on the chat using all the keywords that we've talked about, which is really good. So for this one, friction causes electrons to move from the rod and onto the cloth. The charge on the rod is positive because it has lost electrons, and the charge on the cloth is negative as it has gained electrons. So the key idea here is to include in your answer that the movement of electrons, the transfer of electrons, is the reason for the rod and the cloth becoming charged. So again, it's that transfer of electrons that allows this static electricity and this electrical charge to happen. And if you want to know where you'd get all 4 marks, the first one would be saying that friction is the reason that the electrons move. The second one would be that the charge on the rod is positive because it loses electrons. The third would be the charge on the cloth is negative as it has gained electrons. And the fourth would be, and this therefore allows them to become net positively charged or net negatively charged. Okay. And that is quite a common question that comes up time and time again. It's the acetate rod with the cloth, and you just have to explain how they become electrically charged. Okay, now after charging them, the student moves the acetate rod and the cloth closer together. Okay, so that he moves the acetate rod and the cloth closer together. So which statement is correct? Will there be a force between the acetate rod and cloth, or will there be no force? Great, statement 2 is absolutely correct. There will be a force of attraction between the acetate rod and the cloth. So because one is positively charged and one is negatively charged, as you bring them closer together, because they are different charges, they attract. And that's what you would write in the give a reason for your answer part. There would be a force of attraction because they are different charges. Okay. Okay, so this one talks about the Van de Graaff generator. Before it's switched on, the metal dome has no charge. There's no kind of reason for it to have charge. After it's switched on, then it becomes positively charged. But how can an uncharged object become positively charged? Now, this one is quite tricky because we haven't said it kind of directly, but try to work out how this uncharged object may become positively charged using the ideas that we've talked about. Okay, so some really great answers in the chat, again, using all the key words and all the key ideas that we've talked about. So for this one, there is friction between the dome and the object and the other object that it's touching or rubbing against. The friction causes electrons to be rubbed off from one material to the other, and this means that we lose electrons and it becomes positively charged. Okay, so again, it's that transfer of electrons, it's that loss of electrons that allows something to become positively charged. Okay, so the transfer of electrons, once again, it's really, really important. Okay, so hopefully we can do this one now. We've talked quite a lot about Van de Graaff generators. So the longer the Van de Graaff generator is switched on, the more charge there will be on the metal dome. Okay, now we've got a sentence here to kind of gap fill. So the amount of charge on the metal dome is increased, which causes the potential difference between the metal dome and the earth sphere to what? Okay, now what this means is that we've got a metal dome here and an earth sphere here, and there's electrons between them, so the transfer of electrons between them. Remember, the electrostatic force is a non-contact force. Okay, so they don't need to be touching for the earth sphere to feel the force of the metal dome, to feel the positive charge on the outside of the dome. They don't need to be touching. Now, the transfer of electrons creates a potential difference. Okay, so the amount of charge on the metal dome is increased, which causes this potential difference between the metal dome and the earth sphere. So it causes a potential difference. But if we increase the charge on the metal dome, what do we think happens to that potential difference? So if we increase the charge, if we have more charge, do we think the potential difference is going to go up or down? Remember, potential difference is another way of saying voltage. So we haven't, again, explicitly said the answer to this one, but hopefully you can use your physical intuition to have a think about what might happen to the potential difference. And I can see loads of you saying increase, which is really great. The amount of charge on the metal dome, if it is increased, then the potential difference is also going to increase. Okay. And this does indeed use the idea that we covered yesterday, the equations that we covered yesterday, if you were here, which relate charge, voltage, power and energy together. And here it is. So if you weren't here yesterday, we did go through the energy transferred, charge and potential difference equation. So this is the equation that links them all together. So don't worry if you weren't here yesterday, just follow the question. It kind of gives you the equation and try to think about what you might plug into each part of the equation to get the answer out. So when the potential difference between the Van de Graaff generator and the earth sphere is 60 kilovolts, the spark jumps between the metal dome and the earth sphere. Okay, so we're getting a spark jump to the earth sphere. Okay, now the spark transfers 0.00025 coulombs of charge to the earth sphere. Now you've got the equation here for you, and you need to decide which value goes where. So we're trying to find energy transferred, having been given the charge and the potential difference. So we can see that the charge here, we have 0.00025 coulombs of charge and 60 kilovolts as our potential difference. Now be really careful here first, before we do anything, we need to transfer our 60 kilovolts to normal volts. Okay, so change 60 kilovolts into normal volts. So how do we go from 60 kilovolts to normal volts? Put your answer in the chat if you know. How do we go from kilovolts to normal volts? Great, we times by 1,000. So make sure that you do that first to get your answer in volts. And then we should end up getting 60,000 volts, which you can then times by your 0.00025 coulombs of charge. And when you do times them together, you get 1.5 joules out. Okay, so very well done if you said that. That's using an equation that we have covered before, or maybe not if you weren't here yesterday, but it's using an equation that we know and applying it to a unfamiliar situation. So it can be quite tricky at first, but well done to those of you who are getting the right answer. That's really great. Okay, so I'm gonna stop there for a few minutes and ask you guys if you have any questions, put them on the chat or put them on the Q&A, and we'll take a few minutes for questions, as many questions as we have. I'll try to answer them all.
Yeah, cool guys, and just let us know if there's anything you'd like Preshayla to go over that we've gone through already. I'll just let you know of a few questions that have come through throughout. Someone asked at the very beginning of the session, why do different insulating materials charge at different rates?
So it's due to properties in the material that means that they charge at different rates, and it is quite complex properties of the material. So I won't go through them in too much detail, but if you did want to have a go and research it for yourself, it's about the resistivity, so resistivity and conductivity of the specific material that we're talking about, that allows it to charge faster or indeed slower. Okay, so resistivity and conductivity, if you wanted to go away and research that for yourself, but it is kind of degree A-level stuff, so don't worry if you don't understand it, but that, if you're curious, is how we have different rates of charging in different materials.
Great, and there was a question on one of the first things you were looking through, I think it was just after that, was how would you be affected if you were sitting down rather than standing up?
So there wouldn't be much difference at all, as long as you have your hands on the generator and your feet on the floor. It's not going to be much different.
Cool, and let's have a look. As the machine runs, does the electric field expand or does it have a fixed radius?
So the electric field doesn't expand because it's a fixed charge. But as we get more and more charges, so if you remember, if the Van de Graaff generator has been switched on for a long time, the charge builds up more and more. And if we have more charge, the electric field is stronger. So although it doesn't expand, it does get stronger. Okay, so the electric field can't expand, it just gets stronger.
Cool. Few more questions. So someone's asked, what is the best way to answer experiment type questions in an exam?
Okay, so experiment type questions in the exam are one of the most important because they are usually worth the most amount of marks. So they're usually going to be 4 to 6 marks. So an experiment type question that you might come across in this topic, so in static electricity, would be the rubbing of the acetate cloth the acetate rod with the cloth. So that's kind of the experimental question that comes up time and time again in this topic. But the best way to answer them is to set out your kind of experimental procedure in really clear, logical steps. So you kind of want to go through the steps as if you're talking to a person who's never done or seen this experiment before. Okay, so really break it down for them, really go through each step logically and clearly, making sure that the one before links to the one after, talking about your control variables, your variables that you're going to change, so independent and dependent variables. Are you going to plot a graph? What are you going to find out from the graph? What is your procedure? How will you make it a fair test? Okay, so all really important things that need to be included in an answer, as well as sometimes in a question it might say, explain your answer logically and clearly or coherently, whatever it says. That is where we need to be careful about our spag. Okay, so you need to be writing in full sentences with appropriate punctuation, appropriate grammar, because sometimes that is tested as well.
Cool. And then off the back of the question before, a few people have asked what happens if your feet aren't on the floor, but your hand's still in contact?
So if your feet aren't touching the floor, the charge won't build up on the person, so your hair won't stand up. So it's critical for you to be insulated on the floor. So for you to be grounded on the floor and for your feet to be on the floor. Otherwise you're not insulated from the ground and the charge is going to build up on your body and have nowhere to go. So it's absolutely critical that your feet stay on the floor and you're grounded to the floor.
Cool. And a couple of people have asked, how do I know which material will gain electrons and which one will lose? Okay, so in some cases it is simply about learning. So for this one, they give you a diagram. So sometimes you don't need to know, and they give you a diagram and they tell you which one gets the positive charge and which one gets the negative charge. But when it's not specific like that, and they don't give you a diagram, then when we have two rubbing materials, so for example the child and the slide, it doesn't actually matter which ones the electrons go from and which ones the electrons go to, just to know that there is a transfer of electrons, and that is the reason why they get electrically charged. If they're asking for a specific positive or negative charge, then they're going to help you out by giving you a diagram and telling you which one. So you're not expected to kind of and to memorize it, and just to know inherently they will help you out with a diagram. Nice. And someone's asked, is there an actual use of the Van de Graaff generator?
So the Van de Graaff generator is more kind of used in scientific demonstrations and in schools. You might have seen it on open day. Van de Graaff generators don't really have a scientific purpose, but they're there as more of an educational purpose to show you the effects of static electricity and as kind of an apparatus to help explain what goes on in electric fields and static electricity.
Cool. And the question with the child and the slide, we said the child was electrically charged, so is the slide also electrically charged?
So the slide, I don't actually remember the question, I'll have to get it up again. Okay, so here the child becomes electrically slide when he goes down the slide. So no, the slide in this case would not have a charge. It may have been initially electrically charged and lost its charge and transferred it to the child, but here no, the slide would not be electrically charged. It doesn't tell you that the slide is electrically charged, so you shouldn't assume that it is.
Cool. And I think this was about the very last question you were going through. How many marks would this be? A few people were asking.
The very last question. Okay, I don't know where we got to, so give me a second. I think it was this one, which was the last question that we went through. So I think that this would be either, let me have a think. So you get 1 mark for changing it into 60,000 volts, so changing the kilovolts into volts. 1 mark for doing the correct multiplication, and 1 mark for getting the correct answer. So I would imagine this would be 3 marks.
Great. And when you convert to volts, do you always have to multiply by 1000?
It depends what the letter before our unit is. So in our case, it was kilo. Now, kilo means 1000. However, if it was millivolts, so if you had a little m there, then we would need to do a different calculation. So it really depends what comes before the volts, and it is very important that you know the prefixes, we call them, so the little letter that comes before the unit, because the examiners like to put in questions which make you convert first before you do the calculation, just as another way of showing that you are able to pick up on that and know that the potential difference needs to be in volts and not in kilovolts. So you need to know about kilo and milli. They're really the only ones that they tend to use. So if you do see a little k or a little m, then you need to know how to convert between millivolts to normal volts, kilovolts to normal volts, and also from any type of unit, so meters, amps, any of them could have a K or an M before, so it's really important to know how to convert.
Cool, and this may have been answered as we went along because this was quite early on, but someone asked, why do electrons move from the rod to the cloth instead of the other way around?
So in this one, why do they move from the rod to the cloth? Well, that's because of the intrinsic property in the material. So you don't need to know why the electrons go from one material to the other. That's an intrinsic property, and as I said, it's something to do with the conductivity and the resistivity. But the electrons go from one material to the other. So as I said, you only kind of need to know about the transfer of electrons and what losing electrons and what gaining electrons means for the charge.
Cool, I'll just look and see if we have any other questions. There were lots at the end, so thanks for engaging, guys. In the meantime, Preshayla, was there anything else you wanted to go over in the last couple of minutes, or was that all covered?
I'll go for a quick summary of kind of what we have covered today.
Brilliant.
So first of all, we covered static electricity between two insulating materials or two insulators, otherwise known as charging by friction, and the fact that gaining electrons means that we become negatively charged, and losing electrons means that we become positively charged. And then two electrically charged objects, well, if we have two like charges, they will repel, and two different charges, they will attract. Then we went through electric fields and the fact that having a normal charge can create an electric field itself. Then we went through the uses, well, not really the uses, but how the Van de Graaff generator works, and the fact that it combines static electricity and fields, and what will happen to a person if they were to touch it. What happens when we place an electric charge in an existing electric field? Well, it feels this electrostatic force, which gets stronger as we're close to the charge, and that is everything that we covered today, as well as some exam questions which you can find online really easily. There's actually quite a lot of them, so hopefully when you're doing your own practice you'll be able to find loads of great questions to practice.
Brilliant, thank you, Preshayla. That was a great session. Just to wrap up, a couple of general questions. People were asking about a few other subjects, sort of including languages and other subjects as well, and whether we'd be doing any lessons on those. We are thinking about what we're going to expand out into, and thank you so much for all your feedback. And those of you who filled in the survey last week. So we'll update you both in these sessions and via email to let you know when we add new subjects. And we do have our first chemistry session tomorrow morning at 11 AM. So I hope to see lots of you there. And tomorrow's GCSE Physics session will be at 2 PM as well. And it'll be a nice roundup of the topic of electricity with some past papers. So hopefully really helpful stuff for you there, and see you then. And thank you very much, Preshayla, for the session, and thanks everyone for joining, and see you all soon. Bye guys.
Thank you, bye.